page 81, we're looking at the ratio test. So you look at the little blurb there. Usually applies when the variable power when there is a variable power in the numerator or denominator. And I say it's not nth rootable. So you can't apply some sort of root to both the numerator and the denominator. All right. So you look at these examples in and of themselves, that little blurb may not make a whole ton of sense, but when you see the root test, you'll see the difference between the two. It'll start to make a little bit more sense. All right, so to find the ratio, or to apply the ratio test, what we're going to do is find the limit as n approaches infinity of the n plus first term divided by the nth term of the sequence as an absolute value. And if it's less than 1, it converges. If it's greater than 1, it diverges. All right, so let's start off with first identifying a sub n. I'd like to say I paused for dramatic effect. I just kind of brain cramped there for a second. So a sub n is good to go. So a sub n plus 1 would be 2 to the n plus 1 over n plus 1 factorial. Now, what I like to do before I even get started with the limit part of it is a quick little expansion here, because 2 to the n plus 1 is the same as 2 to the nth times 2 to the first. N plus 1 factorial is the same as n plus 1 times n factorial. That's the definition of a factorial, or one of the definitions. All right. So what I can do now is I could jump to my limit, find the limit as n approaches infinity of the absolute value of this ratio that I just came up with. Oh, look at that ratio. 2 to the nth, poor quality n, times 2 over n plus 1 times n factorial over 2 to the nth over n factorial. So you'll see the 2 to the nths cancel, the n factorials cancel, and we're left with the limit as n approaches infinity of a clean 2 over n plus 1. The absolute value would be irrelevant, because if I'm going to positive infinity and I'm only working with sums and positive numbers, I'm only going to get a positive result. All right, that being said, you could rewrite it as the absolute value of the limit as n approaches infinity of 2 over n plus 1. Realize that this is 0 and the absolute value of 0 is 0. All right, which is a number that is less than 1. So therefore, now we just rewrite the sum from n equals 1 to infinity of 2 to the nth over n factorial converges by the ratio test. All right. So, in terms of abbreviations, can't really think of anything other than just say, if you want, or lowercase a t, the rat. All right. The rat versus the rot, which will be the root test. These are personal abbreviations. I actively discourage you from breaking these abbreviations out in your next class to try to impress your teacher. They're going to be like, what fool came up with those? You'd be like, oh, my professor from last semester. And you'd be like, well, he's what I just said, a fool. And I'd say, well, I just wanted you to write less. So there we are. All right. So next up, a sub n plus 1. Obviously, we're looking at something a little bit more complicated. You probably don't need me to tell you that, just by looking at it, you're like, oh, this has definitely got more stuff in it. All right, but the idea here is to kind of break things up as much as possible. All right, so I'm going to rewrite this as, I'll leave the n plus 1 squared alone, but 3 to the nth times 3 to the first times 3 to the first. Well, that I could just write as 9. Over 2 to the nth times 2 to the first, which is just a 2. All right, so it's that ratio. So copy. It's a ratio of another ratio. So it's a complex fraction. In most of these situations will be complex fractions. So that, oh, that's not a marker. This in ratio form compared to n squared 3. Now this 3 to the n plus 1, I'm still going to write that as 3 to the nth times 3. It'll make it easier to cancel some stuff out. And we're finding the limit as n approaches infinity. All right. So cancel all that is cancelable. So gone, gone. The 2 we're stuck with, 3 goes into 9 3 times. All right. Now, it may sound very picky, but it's actually for a very good reason. If you forget to write the limit part, you're not actually applying the ratio test correctly. Because what a lot of people will do is they'll write all this stuff, they'll do all the algebra and not write the limit. All right, all you're showing me is that you can follow algebraic steps. You're not really showing me that you know why you're doing what you're doing. All right. So make sure you have that in there, otherwise you're going to lose a significant amount of credit. So I'm going to rewrite limit as n approaches infinity, absolute n. I'm going to write this as n squared plus 2n plus 1 multiplied by the 3 over, with a keep change flip, it's going to be 2n squared all right, cleaning it up a little bit further, 3n squared plus 6n plus 1. Again, another instance where the absolute is not going to be relevant because you're taking the sum of everything that's guaranteed to be positive because you're going out to positive infinity. But just in case that's not obvious, you always have the ability to transcend the limit with whatever the operator is. So 3n squared plus 6n plus 1 over 2n squared. So whether you're using L'Hopital or if you're using a graphing technique or whatever, just if you're using a graphing technique, you gotta give me something here. All right. So just give me a sense of, on a test, give me a sense of how you knew what the limit was. All right, because especially with online courses, and I know not everybody accessing these videos will be doing it as part of an online course, but if you are, there's always that question of, all right, how'd you get that answer? Did you get it because you knew it, or did you get it because the internet knew it? All right, so give me a reason. Whether it's the graphing technique, if it's a graphic technique, just throw in a quick sketch. Not really asking for a whole heck of a lot here. Maybe for something like this, the sketch could be a little bit much, but you know, it's nothing too crazy. So 3x squared plus 6x plus 1 divided by 2x squared. You know, I just got to get the zoom right. It's just when I'm using the touchscreen, it's obviously a little different than your handheld. You just do a zoom 6 and you're good. But something like this, just give me the scribble. Honestly, I don't even know if I could physically draw the scribble, but I'll try. Oh. Alright, and so this is to infinity. This is probably, I mean, now that I'm thinking about it, this should be an asymptote, which sometimes it gets connected, so I'll make it dashed. Alright, but that's what we're really looking at. And so that's why we have a three halves. Alright, just give me something. Alright, if you want to use end behavior model, you can do that too. I'm even going to reduce this in size. End behavior model is pretty simple because all you're doing, in terms of showing work, I mean, sometimes it's a little bit more complicated in terms of the understanding, but the end behavior model is you're taking the leading terms, dividing them, and finding the limit of that. Limit as n approaches infinity of 3 over 2 is the absolute value of 3 over 2, which is 3 over 2. All right, now going back to the directions here, or the conditions, if your limit is more than 1, it diverges. So it diverges by the ratio test. So now we're getting into like the height of laziness here, but it is what it is. So the limit, it's not a limit, the sum from n equals 1 to infinity of n squared 3 to the n plus 1 over 2n squared 2n squared 2n squared, no, what am I looking at here? 2 to the nth diverges. Yes, diverges. Alright, so that's that. You know, it kind of spilled into the part C area, but part C won't need as much space, so we'll be good there. Alright, so we're looking at a sub n plus 1. So it's going to be n plus 2, really. Factorial over 3 to the n plus 1. All right, now this is the same as saying n plus 2 times n plus 1 factorial over 3 to the n plus 1. However, like I've been doing before, let me just skip that step and write it as 3 to the nth times 3. All right, so we're looking for the limit as n approaches infinity of this n plus 2, n plus 1 factorial, 3 to the nth times 3 over n plus 1 factorial over 3 to the nth. So lots of nice cancellations here. So this is going to just be an n plus 2 over 3. And that is certainly going to infinity. All right, which is certainly bigger than 0. All right, so therefore the sum from 1 to infinity of n plus 1 factorial over 3 to the nth diverges by the ratio test. All right. Now on page 82, we're looking at the root test. This applies when we're dealing with a series that is nth rootable. All right, so what we're going to do is we're going to find the nth root of the top and bottom and then determine if the limit of that new expression is less than 1 or greater than 1. All right, so we'll jump right to it. So we're going to find the limit as n approaches infinity of the nth root of the absolute value e to the 2n over n to the nth. All right, now the absolute value we're not going to really have to worry about, and a couple of reasons. One, and really the main one, is because we're going down to the positive infinity, just like it was the case for the ratio test. All right. The other, nope, what happened there? The other is most of the, I mean, at least half of the time, I guess, we're looking at instances where we would have imaginary results if we had negatives under the radicals. So, but it's really more the infinity part that we're concerned with. All right. So we're looking at the limit as n approaches infinity of e, really just dividing each exponent by n. So e to the second over n. All right, so this is a constant over infinity, so this is going to 0. And so therefore, the sum from n equals 1 to infinity of e to the 2n over n to the nth converges by the root test, which I abbreviate as ROT. So, second one, limit as n approaches infinity of the nth root of 3 to the n plus 4 to the nth over 2n. All right. Oh, sorry. Wrote incorrectly. I was like, that's not nth rootable. Top and bottom. There we are. Mine's playing tricks on me. So limit as n approaches infinity. And I didn't put the absolute values in here because, it's the same idea as before, where they didn't serve any relevant purpose, because if we're going out to infinity, it's going to get more and more positive. All right, so you can ditch that part if you so choose. 3 to the nth plus 4 over 2n. And so that's going to go to 3/2. And so the sum from n equals 1 to infinity of 3n plus 4 over 2n to the nth, bigger than 1, so it diverges by the root test. And again, for any limits, you just give me some sort of justification for it, whether it's a calculator approach or otherwise. For anybody using digital inking, there's nothing wrong with doing a quick screenshot of your graph and popping it into your work and submitting that also. All right. The whole thing in C is raised to the nth power. After a fashion, is raised to the nth power. So limit as n approaches infinity. Why on earth did I write that? I don't know. I was going for a radical symbol. Cotangent as an inverse of n. Whole thing raised to the 2nth. All right, so divide my exponent by n. So limit n approaches infinity of 1 over. Now for this one, just to make sure I'm being clear about this, there are reasons why we don't have to put the absolutes. In this case, the reason why I'm not putting an absolute is because we have the power of 2 is the only thing that's going to be remaining after the ends cancel each other out. So when you raise something to an even power, the result is always positive. So I'm not worried about the absolutes at that point. All right, so there's some things happening behind the scenes that are sort of taken care of. All right, so for this, what I can do, because again, the operators transcend the limit, so I can say that I have the limit as n approaches infinity of 1 over the inverse cotangent of n as an entire expression squared. So whatever that limit is, I can raise that to the second power. All right, so what I can do is I can handle it a couple of different ways. The inverse cotangent is kind of a weird thing to put in your calculator, but you might remember from way back when we were talking about inverses that if I wanted to do something like, let's say, let me just actually come out of here for a second. Let's say I wanted to find the inverse, well, I'll say the inverse cotangent of, let's say, just a 1. All right. Actually, no, that's probably not a good example. Let me do inverse cosecant of 2. All right. So I'll just kind of pull that off on the side. So we'd say, and I'm talking about it on the calculator. So example, I wanted inverse cosecant of just a 2. All right. The way we would handle that is by finding the inverse of the trig function. I'm sorry, the reciprocal of the trig function. As long as we found the reciprocal of the ratio. Right? And so from there we would say, okay, well, this one here is equal to, it could be pi over 6 or 5 pi over 6. And so that would be dependent on the domain for cosecant, a pathway to come up with the correct answer. And so the domain for sine, it goes from negative pi over 2 to pi over 2. So we would toss this guy and only go with the pi over 6. So this one would be pi over 6. All right, so how does that help us here? If I want the inverse cotangent, I can find, instead of inverse cotangent, I could find the reciprocal function, which is inverse tangent. But instead of n, I would find 1 over n. Why is that important? Well, if I'm using a graphing calculator, not Desmos, I believe, I got to double check, but I believe it has inverse reciprocal functions. But if we're using a TI, or this emulator of a TI, we need some way to get it in terms of sines, cosines, and tangents. So second tangent, 1 over, actually I won't fraction, so 1 divided by second tangent, 1 over n, so 1 over x. And I want that to, I want to see how that goes as I get on out to infinity. Well, it seems like it's increasing without bound. All right. So what I can do is I can get into the table and just verify that that's the case. All right. It does appear to be increasing in a 1-to-1 ratio, but that is the nature of things. All right. So regardless, it's still increasing. All right. So this is going to infinity, and so therefore this one diverges by the root test.